This is chapter 18. My friend Francis, the cat, is sleeping beside me. And we're going to talk about the leftovers of a star. So, we're going to start out with, again, low mass remnants. And we're going to ask, what is these white dwarfs that we've been talking about? If you remember from the previous lectures, the red giants are all fusing hydrogen and helium, and they're leaving carbon in the low mass stars, and the carbon can't fuse quite yet. It's not high enough temperature. And so the outer layers of the star gets pushed out because of this double shell that's formed around them. And these cores are what's left after those outer layers leave. So the white dwarf should be a remnant of heavy elements, carbon and maybe oxygen and other stuff. So what's pictured here is in this one slide is the star Sirius. If you look at it, there's actually two stars there. There's one star is the one that we actually see. Um, oops, is so remember we look at Orion. There's all those stars in the body of Orion, and then you know Orion's a hunter and has two hunting dogs, and in Canis Major is Sirius, is the brightest star. And so in visible light, you just see one star. But in X-rays, you see that there's a second star. All right, it's just a double system. And the second star is a white dwarf. It's called Sirius B. White dwarfs are these remaining cores. They're leftovers when a low mass star uh, produces the planetary nebula, when it ceases all fusion. And that core can't contract any further because of degeneracy pressure, and can't heat up any further because it can't contract. And so it's no longer fusing. It's just a remnant, a big ball of carbon and maybe oxygen. And so because it's not producing uh, any extra energy, it's going to basically stay the same size and it's going to cool off. It can't contract because of the degeneracy pressure. It's going to cool off and it's going to get dimmer over time uh, as it uh, cools. All right, so it goes from white and blue and then through the yellow and red, but it also gets much dimmer. So the ones that it's easy to see are going to be the ones that appear blue and white. So the remnant, and yeah, this overlay didn't work quite as nice. Um, the remnant is going to be about the size of the Earth. Right? A one solar mass white dwarf is about the size of the Earth. That's you know fairly dense, fairly um, contracted, and it'll be even more dense for a higher mass star because what's holding it together that uh, against gravity is not temperature dependent. There's no way for it to heat up. So the higher density, the greater the gravity, the more it contracts. Now, in the white dwarf, the electrons are holding up the material, and the more confined they are, the faster they're moving. All right, this is based on the uncertainty principle. So as they approach a limit, the electrons end up moving faster and faster and faster. All right, and essentially, there's a limit to the size of the star, what's called the white dwarf limit, or the Chandrasekhar limit. I cannot pronounce that, but that's okay.